Welcome to a brand new episode of Greentech Pulse, and today we'll be talking about a topic, battery storage, which I haven't talked about before. Now, battery storage, I'm not talking about the maybe 5 or 10 kilowatt batteries we have in the house. No, I'm talking about large scale batteries, batteries that power cities, that power lots of buildings at the same time. And that's what our guest today deals with. Brian Kane, our guest today, is the Chief Project Officer at Powin, and they deal with large scale utility storage, things like that. And that's what we're talking about today. So, welcome to Green Tech Pulse, Brian.
Thank you, Peter. Thanks for having me.
Thank you so much. So, I think first of all, I was doing a bit of research and I saw that you've discharged about 1 terawatt hour of clean energy. So, I would like to say congrats on that. That's about 34 million homes. And how do you do that?
Thank you. Okay, so Powin is currently has already developed or is developing 17 gigawatt hours of large scale utility energy storage. We're working with 50 customers across the globe, 170 projects. We're a battery systems integrator, so we partner with tier one cell providers. So they produce the cell and then we receive it, package it into a larger system called an energy storage system, and then deliver it to customers, generally developers or independent power producers, and partner with them to interact with the local grid or local solar to charge the batteries and then discharge them at optimal times to create grid stability. So in the very simplest form possible, when power is at lower cost or when the sun is shining or when the wind is blowing, the system is charged to full capacity. And then when the grid demands it, the system is commanded to discharge that energy to provide up to, generally speaking, 4 hours of energy at a given power set point. So you highlighted 34 million homes, nominally 1 terawatt. Another way to think about it is each day we are powering roughly 2 million whole homes across the world for 4 hours. And so it's while there's some complexity to create the system and deliver it, in its very simplistic form, it's a rechargeable battery. And it's leveraged to optimize the performance of other intermittent technologies, for example, solar, which only can generate power when the sun is up, and then dispatch to enable both energy demand as well as grid stability.
Okay, so I think I'll just do a little background, like I said before we started recording. Most times when we are moving through, okay, normally for the normal grid, we have the thermal plants, we have the coal plants and coal burning energy and sending it directly to the grid. But when we are moving to renewables, like you mentioned before we started recording, we have solar, hydro, and wind. And a lot of times, solar, like it produces during the day. Wind, when there is a lot of wind, you have more power. Hydro, the same thing when you have the water moving, and that's why you need battery storage for when, like you said, when it's not when there isn't peak production. So now battery storage, like currently I mentioned that I'm using solar right now. Here I have a 5 kilowatt battery I'm using right now. But when you talk about utility scale, you're talking about powering 2 million houses a day for 4 hours every day. So for a typical project for utility scale battery storage, what size are we looking at? What size are we talking about?
So it's been an interesting evolution. So the when the when we developed our first project, it was 8 megawatt hours. So that's a good size project, 8 megawatt hours, right? That was about 8 years ago. Today, if you average all of the projects that we're currently developing, the average size is roughly 800 megawatt hours. But in some cases, they're delivered. There's a project in Australia, for example, that we're in the process of commissioning with our partner that can at nameplate deliver 1.9 gigawatt hours over a 2 hour period. So at this point, you would, 7 years ago, it was less than 50 megawatt hours. 4 years ago, it was maybe in the 100 megawatt hours range. And now today, the largest utility scale projects are in excess of 1 and 2 gigawatt hours. So our average size over the entire life of our development process, those 170 projects, averages out to roughly 180 megawatt hours, but it's really a bunch of very small ones from the early days, and now a bunch of very large ones from current applications. Now there are other scenarios, for example, in markets where it's a slightly different application. So if you don't mind, I'll sort of re-summarize how you've thought about the way the grid is structured with generation. So there's base load and base generation. So base load is the minimum amount of energy that any given grid is going to consume at its lowest point. And that is generally always powered by some version of nuclear, if you have nuclear in the region, and or coal. And then hydro is generally considered base load. And solar is in fact considered base load. And what I mean by that is solar takes priority over any other peaker generation. So historically, peaker generation is a fast response technology that when the grid changes shape, when people turn on their lights or turn on air conditioning or demand, that system is turned on, generates for a relatively short period of time, and then is turned off. Traditionally, that is a natural gas or a coal-fired plant. Over the last 15 years, it became obvious that there is a optimal and cleaner way to provide that peaker capability, and that is energy storage. So while energy storage enables the smoothing of solar, because solar kind of creates power based on the arc of the sun, it also is a way to use base load that is in excess capacity at night to charge a battery and then dispatch it during the day so you never have to turn on those fossil fuel generators. So it not only enables renewable predictability, it also enables the reduction of need for fossil generation for a number of reasons. So so when we talk about, as I was saying earlier, the application, it provides multiple versions of solving the same problem, which is avoiding the need to continue to start and stop fossil fuel generation for relatively short periods of time.
Amazing. I think that's a new way I never thought of. Like I said earlier, I always learn in every episode. So
Yeah.
I love that. Yeah. So I think so having this battery storage practically eliminates the need for the natural gas and the coal-fired plants at those in peak periods.
Correct. It does that. And then there's another aspect that's super important. So using the United States as an example, generally considered the most robust and reliable grid in the world, as load pockets have grown, Phoenix in Arizona is a great example. The population growth in Phoenix is pretty extraordinary. There's plenty of generation in and around the larger Southern California and Phoenix region. The problem is there isn't necessarily enough transmission and distribution to keep up with the growth in smaller pockets inside that distribution. And transmission and distribution projects are massive. They're very expensive and complex to permit, create rights of way, et cetera. So another thing that energy storage, clean energy storage enables is you can put those devices closer to the load without necessarily having to add more generation. And when load increases on a given distribution point, the stability of the local grid becomes at risk because there's just a greater and greater demand, potentially creating voltage or frequency instability. Having a local load source that was charged when demand was low and then dispatches when demand is high creates both delivers the energy that the grid needs, but um, also creates the stability that the grid needs. So you avoid brownouts for two reasons: one, you're delivering the energy, and two, you're maintaining voltage stability. So it's it's when we talk about utility scale, it's both size, but it's also application that enables the stable operation of the grid, as well as avoiding the need for additional large scale generation remotely from a given site.
Amazing. So apart from storing energy from the grid, are there other things that the Powin's battery systems do? Are there other things it does apart from that, like maybe frequency or voltage or anything supports?
Yeah, so there's a host of ancillary services that are that's the generic term in the business for using power and energy to create a stable grid. So again, when you just think about in its simplest form, the grid is a sine wave, right? Delivered at some voltage, could be high voltage, medium, or low voltage, and a frequency at 60 hertz. If you're in Europe or in Australia, that's at 50 hertz. As I was highlighting earlier, when demand increases, particularly when demand rapidly increases, and so when you're in hotter months in Texas, you're going to see major fluctuations in demand because of maintaining cooling, et cetera. The grid doesn't necessarily need a lot of energy, but that distribution problem I highlighted becomes a problem. So as demand rapidly increases, voltage drops or frequency can become unstable because there's a bunch of generation far away that's trying to react with speed. And the battery system, the energy storage system, is sitting locally at an injection point, and it will automatically respond based on the change in voltage or the change in frequency to inject power for a very short period of time to create the necessary stability and avoid instability. So it uses power and energy to provide stability versus just dispatching for an hour or two or three. The early days of energy storage were more about that than it was about medium duration energy delivery. So today, the grid fundamentally feels that they've got sufficient ancillary services, leveraging energy storage, and has moved further and further into longer term duration, 2 hours, 3 hours, 4 hours for the purposes of energy. And we do anticipate that there'll be even longer duration applications, but the combination of the technology and the economics of longer duration dispatch, let's just call it 8 hours and greater, are still being evaluated as an appropriate technical solution for the grid.
All right, so I think I like what you talked about the different uses of this utility scale storage systems, especially where you talked about these small pockets where previously you'd have had to build a generation plant, but now you just concentrate on transmission and have a battery storage unit there. So now looking at places you've installed these large scale storage plants in before, what are the economic benefits you've seen having them, especially for the grid operators, for the utilities, and also for the final end users, the consumers too?
Sure. So the best way to think about it is there's an ecosystem of utilities and independent power producers, and then of course the consumer who buys from the utility, all of which benefit in a different way from the concept of large scale energy storage. So from a utility standpoint, they have two options. One is they enable an environment where a developer can build a power plant that sells power at high peak demand whenever they need it. And so how that brings value is they know that they've got the resource adequacy to receive the energy when the demand is high, and then the developer can plan on and secure revenues when they deliver that at when demand is high. The challenge with that model is it's not necessarily a predictable revenue stream because weather has an impact on the demand, and different use cases have an impact. So most of the projects at this point are actually a fixed price application, which is called a power purchase agreement. And so what a power purchase agreement represents is some combination of either a direct consumer or an indirect consumer, the utility, and then a generator and a project financier that create an environment where every day there's a guaranteed demand for the energy, such that the utility knows they don't have to go buy energy from somewhere else. So, right, every utility, generally speaking, does not have their own generation. So they work with an independent system operator and IPPs to pay for energy on the spot market. When they have utility scale energy storage within their network, they don't have to pay for that spot market energy. And it's a way for them to avoid higher costs and thus guarantee a better rate to their consumer. Meanwhile, the developer and the project financing company has a predictable return on investment. So just very simplistically, if you have a 250 megawatt project that dispatches 4 hours a day, that's a 1 gigawatt hour guaranteed economic return for a specific price that's predetermined on that day of the year or that day of the month. And so the developer plans an operation and an economic return over a 10 or 15 or 20-year period, and then partners with a large scale investor, could be a bank or some other fund, and the large scale investor provides the upfront capital. The operator generates at that predictable rate with the payment that they get for every kilowatt hour they produce. They use that money to, one, fund their employees, two, create a profit for themselves, and then three, provide a guaranteed return on investment to the large scale investor that provided the upfront capital. So it creates jobs, it creates grid stability, it creates predictable energy pricing for the consumer, and it enhances reliability for all users of the grid that benefit from that technology.
Amazing. So yeah, that answers it. So we have jobs, we have the grid stability, we have predictable pricing, and guaranteed energy. So now looking at implementing those large battery storage systems, I know something like mine is just simple. It's just 16 cells with a BMS, and that's all. But when you're talking about your 8 gigawatt hour, 800 gigawatt hour projects, what unique challenges do you have implementing projects like that, supporting entire communities and things like that?
The basic concept isn't very dissimilar to what you have. So you have battery cells that create modules, and then they're controlled by a battery management system, a BMS. And then the entire site is controlled by an energy management system, an EMS. And then that interacts with a power plant controller, which is the interface to the grid. Powin's unique value is that we provide all of that except for the power plant controller today. So we provide all the necessary hardware and the software to have an integrated, fully operational, large-scale utility system. The challenges that every project faces is when you're talking about interconnecting an 800 megawatt hour system, that amount of energy can literally change the grid's performance. So it provides value and stability when it's working correctly, But if it's not planned and integrated and controlled correctly, it can provide risk. So if you inject the wrong amount of energy or you stop injecting the right amount of energy unexpectedly, the grid has to respond. So one of the biggest challenges that the industry faces is planning an interconnection that ensures that the entire larger network that's going to receive the benefits of this large scale power is designed and controlled to enable its receipt at the point of connection. So it's critical that you have a well conceived software and control solution that ensures consistent connection and stability. And there are rules about there are standards that the devices must satisfy to ensure that they're designed and capable of providing the necessary performance and reliability. But an integrator such as ourselves needs to be very thoughtful about making sure that we design a robust software overlay that's able to interface and be predictably controlled by the commands that it's given.
All right. So I think another area people talk about, especially when it comes to the area of renewables, is the topic of waste, especially when you talk about solar. So we talk about the panels, what happens to the panels after their 10 or 25-year lifespan, and the batteries after their maybe 5 or 10-year lifespan. So for your batteries, for your energy storage systems, can you just walk us through the life cycle? So starting from the project planning to the deployment to operation, and then maybe when the batteries are at the end of their life, the decommissioning. So let's just visualize how it goes.
Yeah, so general large scale project takes roughly 2 to 3 years to plan and implement, at least. And so the long pole in the tent is planning the interconnection with the grid. And then the second long pole is securing the necessary permits after you've created a design. So once you've got the interconnection planned and once you have the design conceived of, a developer will work with someone like Powin to put together the actual physical design of the battery plant. And at that point, they enter into a contract with us. The contract will be issued, and then Powin goes through the process of securing the necessary supply of the cells and all of the other ancillary equipment and materials that are necessary to turn it into a system. The lead time for that process is generally 6 to 9 months. So once you've made a decision to develop, you have all the necessary approvals, you've contracted with an energy storage provider such as Powin, you wait about 9 months, you build the site to receive the equipment arrives, and it's delivered and commissioned over the course of 3 to 6 months. So for us, the general development timeline from contract to system operational is about 15 months. And then after those 15 months, the system is turned into a commercial operating asset, and is actually, most projects are planned to operate for 20 years. So the cells that are leveraged, so lithium iron is the application, the current technology that we use, they are all designed and warranted for a 20-year use case, assuming specific cycling. So in general, 1 full cycle per day. So customers will conceive of an economic return based on that assumption. Some will choose to operate it for fewer than 20 years, but the product itself is expected to be a 20-year product. Now, it's fair to say that the battery recycling industry at scale still has a lot of work to do. But these systems don't just get thrown out, the batteries themselves and the other materials. It's metal and chemicals, and they can be recycled and effectively the core materials can be reused to make more batteries. So again, despite the scale that we're talking about, it's still relatively early in the grand scheme of the long-term life cycle of this technology. But I anticipate in the next 5 or 10 years, we're going to significantly improve our ability to optimize the reuse opportunity for the cells themselves. And so a battery's 20-year life will be the first life, and then there'll be a recycling process, and then you'll be able to benefit from a lot of those same materials for performance again and again.
Amazing. So I think for 20 years, one cycle a day, you're talking about 7,000 something cycles out of each cell. I think
Correct.
which is yeah, very realistic. So now looking at you mentioned that you use lithium ion batteries. I think that's probably the most popular thing right now because that's what I use too. So beyond lithium ion, are there other battery chemistries or storage technologies that Powin is exploring for these utility scale applications?
So yes, so one of we perceive our advantage as being generally DC agnostic. And what that means is we're not married to only being an LFP cell provider. What we're married to is generating maximum value and partnership for our customers. However, the economics say that for at least the next 5 years, LFP up to 8 hour storage duration makes the most financial sense. We are looking at sodium ion, which is a very interesting, very stable technology. As you're aware, some people have mostly statistically unfounded fears of lithium ion batteries. But it's a reality that you have to plan for safety and understand how to mitigate if there's a fault. When we talk about sodium ion, it doesn't have that. The nature of the chemistry doesn't result in those same problems. However, it's roughly half the density and 4 or 5 times the cost today. So we'll always be evaluating whatever may be next to support longer duration storage as well as optimal economic storage. But as of today, there's nothing on the market within the area where we play, which is just called 2 to 8 hour duration projects that can compete with LFP.
Amazing. So I think you mentioned in this answer something which I want to touch to the fears a lot of people have around these lithium ion batteries. And I think that's about the safety, where we see videos and lithium fires, which are really unique in the way that they're hard to put out and they're really stubborn, these lithium fires. So in this large scale setups which you do, what safety systems are required to make these not be a danger where they are installed?
Yeah, so right, so and it's a common theme, but any version of energy storage inherently has some natural risk because it is energy that if introduced to certain conditions the can create a challenge, and that is true of fossil fuels as well as a battery system. So the industry has moved to an adoption of standard safety systems that are designed to prevent an event. So that's just proper thermal and voltage management. So if you get outside of certain parameters, you stop operating the battery. And then in the event that there's a problem, there's fire suppression and anti-explosion type solutions. So a battery in and of itself, by definition, doesn't just combust or explode. But if in the right conditions, if you don't have a safety system that can manage a failure appropriately, you can create an environment where the gases are to the point where it can create an event. So every system, not just Powin's, is designed to identify the potential for the existence of gas and a failure and then evacuate it. And then also, you're constantly monitoring the temperature of the system and the voltage of the system, as I said earlier, to ensure that if you're detecting an anomaly, you simply stop operating the battery. Statistically, it is extremely unlikely to actually have an event. But unfortunately, when there have been some events, they've been very public, and it feeds the perception that there's significant risk. But the data actually confirms that it's not a significant risk. It's just a risk that needs to be managed like any others.
Amazing. So I think you've adequately covered that because most, like you said, most batteries come with the system to monitor the temperature for thermal runways and things like that. So, like you said, it's not really a big risk like we tend to take it. So, for utilities or large energy users who are considering your size of battery storage solutions, what advice would you give them about getting started with this?
Um, uh, Number one, understand the resilience and capability of the local distribution network to receive an injection that is coming kind of from the other side. Like as I was describing, normally generation's far away and then it's consumed at the source. Two, understand the probability and the safety of the system. It's extremely high. Don't let anecdotes or suggestions create resistance to considering the benefits of the technology. Three, spend time with your local community to help them understand the benefits of the system. And then four, identify a contract structure and partners that know what they're doing, right? So someone who's developed 17 gigawatt hours of energy storage coupled with a construction company that's developed under several versions of renewable, whether it be battery or solar or others. And then lastly, an operator that's going to be a long-term partner and that's committed to developing a reliable solution that provides the technical and economic returns that we talked about earlier. Do your homework, essentially.
Exactly. Do your homework before getting started. So now for as we get to the end of this episode, we've talked about a lot of things about large scale utility energy storage. But is there something that you'd like to leave with the listeners, probably that I haven't talked about, but you feel would be important for them to know?
Um, Primarily that this is an enabling technology. So in across the world, there is a goal to get to 100% renewable. And there are lots of folks who resist the concept, who, whether it be for business or, what they believe to be valid scientific reasons, argue against the practicality or the cost effectiveness of renewable energy. There are challenges that need to be contemplated, and there is real value leveraging fossil fuels under certain circumstances. But energy storage, as I just described it earlier, with the ability to recycle and reuse, is a bridge to any version of generation. So whether it be some version of a very clean fossil consumption or some version of 100% renewable, this application is necessary in all cases. Because what you don't want to do is need to spend billions of dollars to move energy around when you could, in fact, invest smaller bits at the right points in the system to capture energy and deliver it back again when it's most required. So the point being, this enables renewable energy, But truthfully, the best way to think about it is energy storage enables reliable energy and load growth in any key sector. For example, with the oncoming AI boom, there's no question that utility scale energy storage is going to be at the forefront of enabling the rapid and clean development of those new load pockets. So it solves many, many issues. It's in the renewable energy space, but most importantly, it's in the reliable energy solution set.
Amazing. So now for listeners, for people watching who would like to continue this conversation, would like to get in touch with you, in touch with Powin and learn more about what you do, or maybe work with you, what's the best way they can reach you?
Well, we certainly have a website, www.powin.com, where you can access our contact phone number and general information email. And I'm certainly available on LinkedIn and can be contacted that way. So I would suggest that you go to our website or find other mechanisms to reach out to myself or my colleagues. On LinkedIn. We have operations in North America, the Asian Pacific, and the general European and Middle East market. So we have people across the globe that are available to partner with developers, utilities, and just interested parties to understand how they can best benefit from the technology we provide.
Amazing. So powin.com, connect with the team, connect with Brian, connect with the team on LinkedIn to continue this conversation. And if you learn something, I've learned a lot from this episode. If you've learned something and you know someone who will benefit from this episode, share it with them. Until next week when we're back with a brand new episode, see you. Bye for now.